Thank you. You need a solid state detector because they get so you have to still capture the particles. And these go up to maybe a MeV. And then you have instruments, another separate instrument to measure the electric field. Usually wire booms on a spinning spacecraft, and you measure the potential difference from one side to the other. And that's what, if you were here last week, Stuart talked about in his solar wind talk. And then a few other ones that measure high frequency waves. These are up around electron plasma frequencies. And so combining them all together, you hopefully get a complete measurement of, or diagnostic of what the plasma is doing. But as was said last week, there's not yet really been a space plasma physics mission that had everything in the right place at the right time. Each one has had advantages and disadvantages in what it can do. So this is the data that you get, and then this is where you take it. So for example, with cluster, you have an orbit which is polar. Its perigee is about 4 Earth radii, and it goes out to 20 Earth radii. And what you have to imagine or remember is that the plane of this orbit, as it turns out, is fixed in inertial space. So as the Earth goes around the Sun, the orbit appears to precess around the Earth. And the precession goes at about 1 degree per day, because 360 degrees in 365 days. So that means that if you place it in an orbit in August, where the apogee is in the tail, then a few months later it's moved around to the dusk flank, and then into the solar wind, and then back around again. So that means that you can only study magnetotail reconnection for a few months a year. And the final issue that you have to remember is that I said they were flying in formation for spacecraft, but the mission plan changed the scale of the tetrahedron periodically. So at the beginning, they were separated by, in the tail, which is this, so this is time from January 2001 up until the present date. The circle and the square means cusp and tail, but concentrate on the green squares. So for the first season, the separation was about 1,000 kilometers. It turns out in the Earth's magnetotail, 1,000 kilometers is of the order of the ion inertial length. It was a bit bigger. This is a logarithmic scale. It was a bit bigger for the second one. For the third one, the separation was only 200 kilometers or so. And so then it varied depending on different teams having different science objectives, and this all being folded together into the plan for the mission. And then they started to do different things after they varied the size as much as they could think, to then have different separations between different spacecraft. So what do we know about diffusion region in the Earth's magnetotail? It's only in the last, 13 years that we've actually made the observations. And it started in the late 90s with data from Geotail, and Nagai, Fujimoto, Asano, who demonstrated the existence of Hall currents around the separatrices, and they would see a flow reversal that would be going from one side of an X line to another. And then the real, I think, key paper that everybody looks at is taken from another spacecraft called WIND, and this was published in Nature in 2001 by Oriset et al. And they really established that the WIND spacecraft flew through the ion diffusion region in the magnetotail. And they saw the Hall fields, and this strongly established that Hall reconnection was occurring in the magnetotail. And so since then, Cluster, in the last 10 years, has really been in the vanguard of providing new spacecraft data that's helped to test and develop theory. And there's a very nice review by Götz Paschmann. It's only 5 pages long, so you can read it in a morning or less, in Geophysical Research Letters that was published in 2008. And this basically summarizes what we've learned, or points to the papers that have been published in the last few years. The progress is almost entirely by case studies. And the reason for that is because the diffusion region is small and the Earth's magnetotail is big, and if you encounter it, it's essentially a matter of chance. You're flying through this region. We know that reconnection occurs basically somewhere around here. But whether or not it happens when you're there depends on how the magnetosphere is loading and unloading, what the solar wind is doing, and also there are more technical aspects like were your spacecraft instruments switched on in the right mode, transmitting the data, etc., etc., etc. So Justin called it an ergodic system last week, but it's really more, you just have to wait and collect data and see what you get, and over time accumulate events. And so that's why the first studies were all basically, we saw it in the data and then we were able to analyze it. Now, the problem with case studies is that you tend to pick exciting events, and so is that representative of the average? And how many are there really? How have we actually got? And then that provides an experimental database to take forward. So what's the average picture? And so what I had done is to basically go through the cluster data and look for and do a survey to see what have we got and what is the average properties. So in the end, I looked at the 5 years of data. The reason for this is basically technical and to do with where the orbit went, and I won't go into it now, but I can talk about it afterwards. And then essentially do a sort of sieve survey of the data. You start looking for, well, were they near the current sheet in the magnetotail? And then did we see a flow burst that would correspond to a reconnection event? And then did we see a flow burst that reversed direction that meant that we were going through from one side of an X-line to the other? And cut it down, and how many events do you get? And it turned out in the end 33 events, which is not a lot. Now, that's not to say, this is not a comment necessarily on how often reconnection occurs. In fact, it definitely isn't a comment on that because, of course, it depends on the orbit of the spacecraft. If a spacecraft goes in the wrong place, you won't see as many events as if it was in an optimal place. I think now there's an argument that cluster's orbit should have been at a higher apogee for this science. But then again, cluster was designed to do a lot of different science, and everything just ends up being a compromise. So this is what we've got. And then with the multi-spacecraft data, you can do an analysis and really try and see, are the jets, does the structure fit an X-line? And there are various other technical issues that I won't go into, which means that you can't do a multi-spacecraft analysis on all these events. But on the ones you can do, almost all of them are an X-line, and one was an O-line. So basically, these events are X-line crossings. Sometimes you see them in pairs. So you definitely do get multiple X-line reconnection in the magnetotail. So two X-lines occurring near each other in the current sheet.
How do you figure out that it's an X-line? How do you figure this out? I mean, you say this is an X-line. So what's the
procedure? You look at the data.
But what does it tell? What is it that you measure?
It's actually not
How do you know it's an X-line?
terribly complicated because you are in the paradigm of seeing a earthward flow changing to a tailward flow. And so in the simplest level, you have multiple spacecraft and you know where they are. And if the one that's earthward sees the earthward